Electricity plays such an important part of our daily lives that we aren't even aware of it. Only when the supply is interrupted do we realize how much we depend on it. Click on the circuit breaker switches. Introduction. In this lesson, you will be able to understand electric current as the rate of flow of charges, understand the mechanism of conduction of electricity in metal, understand the drift velocity, derive and use the equation I equals NEAV and know the typical order of drift velocity. Define current density J and the equation J equals sigma E. Click the switch to complete the circuit. Current is the flow of negatively charged electrons. By convention, the direction of the current is taken as the direction of flow of positive charge. This is in the opposite direction to the electrons. Click the current direction button and the flow of electrons button. The current is the rate of flow of charge and it is measured in ampere or coulomb per second. Click on the symbol for current I. Click on each stage of this worked example. Summary. The direction of the current is taken to be the direction of the flow of positive charge. This is opposite to the direction of the flow of electrons. Electric current is the rate of flow of electric charges. I equals dq over dt. Unit of current is ampere, which is equivalent to coulomb per second. In metals, some electrons are not used in bonding. These free electrons move randomly throughout the metal. Click the Track Electrons button to observe the motion of 3 specific electrons. What is the net flow of the 3 electrons which have been tracked? Answer: there is no net flow in any specific direction. We can see the random motion of the free electrons showing that there is no net flow in any particular direction. The average speed of this random motion is in the order of 10 to the power of 6 meter per second at room temperature. Does the random motion of free electrons produce a current? Answer: no. The average velocity of the free electrons is 0. Thus, there is no net flow of charge. As a result, the current is 0. When there is no electric field applied to a conductor, the free electrons move randomly. To apply an electric field to the right of the conductor, click and drag the slider to the left and release the slider at different positions. Observe the movement of the free electrons as the field strength changes. If the field is to the right, what direction will the free electrons drift? Answer: the free electrons will drift to the left, opposite to the field. Now click and drag the slider to the right and release the slider at different positions? Why don't the electrons drift in the same direction as the field? Answer: by definition, an electric field shows the direction in which a small positive charge would move. Electrons are negatively charged, so they move in the opposite direction to the field. Click the Track Electrons button. Describe the net movement of the 3 electrons which have been tracked. Answer: there is a net flow of free electrons in the direction opposite to the electric field. In the electric field, the free electrons will move with an average velocity known as a drift velocity. The magnitude of drift velocity is typically around 1 mm per second, whereas the average speed of the electron's random motion is around 1000 km per second at room temperature. The relation between the drift velocity v and the current I is given by I equals NAVE. Click on the switch to close the circuit. Click the derivation button to see how the relation is derived. Click the Current Density button. The current density is defined as the electric current per cross-sectional area. It can be shown that the drift velocity of the free electrons is directly proportional to the current density. Copper has a density of 8.9 times 10 to the power of 3 kg per cubic meter and a relative atomic mass of 64. A particular copper wire has a cross-sectional area of 0.10 square millimeter and carries a current of 4.0 ampere. Calculate the number of atoms per cubic meter. The number of conduction electrons per cubic meter in copper. Assume that each atom contributes 1 free electron. The drift velocity of the free electrons for this current. The maximum safe current density for any wire made of copper is 1.0 times 10 to the power of 7 ampere per square meter. Calculate the drift velocity of these electrons when the current reaches this density. Summary: if no battery is connected across a metal conductor, the free electrons are moving randomly at very high speed due to their thermal energy. On the whole, there is no net flow of free electrons, thus the current is zero. When a potential difference is applied across the metal conductor, the free electrons will move with a very small average velocity, known as the drift velocity, v, toward the positive terminal of the battery. The relationship between the current and drift velocity is given by I equals NAVE, where N is the number of free electrons per unit volume, A is the cross-sectional area, and E is the charge of 1 electron. The relationship between the current density, J, and drift velocity, V, is given by J equals NEV. Click Switch. The resistance of a conductor is directly proportional to the length L of the conductor and inversely proportional to the cross-sectional area A of the conductor. Click the Resistance button. The reciprocal of the resistivity is known as the conductivity of the material. Unit of conductivity is per ohm per meter. Click the derivation button to derive the relationship between conductivity and current density. The conductivity of aluminium at room temperature is 3.13 times 10 to the power of 7 per ohm per meter. Assuming that aluminium has 5 times 10 to the power of 28 free electrons per cubic meter, calculate the drift velocity of the electrons if a potential gradient of 1.0 volt per meter is applied across a wire made from aluminium. Click Step to check your answer. Summary. The resistance of the conductor is directly proportional to the length L of the conductor and inversely proportional to the cross-sectional area A of the conductor. The resistivity of a material is given by ρ equals Ra over L. The reciprocal of the resistivity is known as the conductivity of the material. The electrical conductivity, sigma, is related to current density, J, by the equation J equals sigma E, where E is the electric field strength.